Good day, everyone. Today we're looking at the first derivative test, section 5.3 in your book. The objectives are to determine intervals for which functions increase or decrease, and to use the first derivative test for local or relative extrema. Here we have a generic function with 5 critical points identified. 4 of those points, the first, second, third, and fifth, are critical points because the derivative has a value of 0. The fourth critical point is critical because the derivative is undefined. Also note that critical points 1 and 5 are not extrema. And the reason they're not extrema is because the sign of the derivative does not change. For critical point 1, if you look at the region both to the left and to the right, you will notice that the derivative is positive. For critical point 5, to the left and to the right, the derivative is negative. Because there is no sign change, these two critical points, 1 and 5, are not extrema. This is not the case for critical points 2, 3, and 4. For each of those, we have a switch. In critical point 2, goes from positive to negative, as critical point 4, same thing. Critical point 3, on the other hand, goes from negative to positive. Here is the first derivative test for local extrema. This test applies to continuous function f of x at a critical point C. If the derivative changes sign from positive to negative at C, then f has a local maximum at C. If it changes from negative to positive at C, then f has a local minimum at C. If the derivative does not change sign at C, then f has no local extreme value at C. Now we're going to look at each of the 3 cases in more depth. If the derivative changes sign from positive to negative around a critical point, we classify that point as a local or relative max. Notice that this classification holds for both types of critical points, when the derivative is 0 and when the derivative is undefined. For the second case, the derivative changes sign from negative to positive. This indicates a local minimum. Again, it holds for both cases when the derivative is 0 and when the derivative is undefined. The third case is if the derivative does not change sign at C. In other words, it has the same sign on both sides of C. In this case, f does not have a local extreme value at C. It is neither a max or a minimum. On to the examples. For these examples, we're interested in finding relative extrema for the functions. Relative extrema only exist at critical points, and critical points are identified by setting the derivative equal to 0 or figuring out when the derivative does not exist. For this example, the derivative is 2x minus 2. Setting it equal to 0 yields a critical value of 1. Since the derivative is a line, 2x minus 2, it has no point where it does not exist, leaving x equals 1 as the only critical point. Next, we set up 2 intervals around our critical point at 1. We're interested in points less than 1 and in points greater than 1. This table will help us in our analysis of this function. First column is the intervals. The second column contains the function. Note that for x is less than 1 and x is greater than 1, I have a dashed line going through it, meaning that we're not going to do anything with those boxes. We are interested in what the derivative is doing at those 3 points, at those 3 intervals, and we have a column for our conclusions. First box we can fill in is at x equals 1. At x equals 1, the derivative is 0. The value of the function is 1 at x equals 1. Now to focus on the derivative column. For each of the intervals, we're interested in the sign of the derivative, not necessarily a specific value. For the interval x is less than 1, I selected the point x equals 0 to evaluate the derivative. Notice that at 0 the derivative has a value at -2, so for all points less than 1 the derivative is negative. Next, I test a point greater than 1. Shown is x equals 10, but you can pick any point you want. Again, we're not interested in the actual value of the derivative itself. All we care about is the sign. In this case, at 10, the derivative has a value of positive 18, so we indicate a positive for the derivative column at the interval x is greater than 1. Next, we begin to make conclusions on what we have so far. For the interval x is less than 1, the derivative is negative. This indicates that the function is decreasing. For our other interval, when x is greater than 1, the derivative is positive. This indicates that the function is increasing. Next is our critical number x equals 1. The derivative switches from negative to positive. This indicates that the point x equals 1 is a relative minimum of the function f. If we look at a graphical representation of the function, we see that the point 1, 1, which we had identified as a relative minimum, is actually a global minimum. The next example that I would like to look at is x times the square root of 18 minus x squared. I have rewritten it to make the computation of the derivative a little bit easier. Here is the first part of the derivative. Notice that we have to use product and a chain rule. Second version of this derivative combines the terms 1/2 negative 2x and x squared for the second part of the derivative. To find critical points, we're going to have to set this derivative equal to 0. The way I have chosen to solve this is by adding x squared times 18 minus x squared to the negative 1/2 power to both sides. I set up a proportion with the negative exponent dropping down to the denominator for the piece on the right. Next step is a cross multiplication, yielding 18 minus x squared equals x squared. Adding x squared to both sides and dividing by 2 yields 9 equals x squared. This last equation yields the critical points 3 and -3. The next step is to investigate what the derivative is doing for intervals surrounding these critical points. The value of f at -3 is -9. At +3, it's +9. Since these are the critical points, the derivative has a value of 0 for -3 and +3. As with the previous example, we're only interested in the sign of the derivative across these three intervals. For the interval x is less than -3, I have selected -4 and have shown the calculation. That number turns out to be negative, so the derivative is negative on the interval x is less than -3. For our second interval between -3 and 3, I have selected x equals 0 and have shown that to be a positive number. It is positive because the second term goes away. 0 squared is 0, and 0 times that second term is 0 no matter what, leaving the first term as 18 minus 0 squared, which is 18, and the square root of 18 is some positive number. For the interval x is greater than 3, I have selected 4. I have not shown the calculation of the value, but it is exactly the same as is the case for f of for the derivative at -4. With the signs of the derivative in hand, we can begin to fill out our conclusions column. For the intervals x is less than -3 and x is greater than 3, the first derivative is negative. Because it's negative, the function is decreasing on these intervals. For the middle interval between -3 and +3, the derivative is positive. This indicates that the function is increasing. The first critical point, x equals -3, is a relative minimum since the first derivative switches signs from negative to positive. The second critical point, at x equals 3, is classified as a relative maximum since the first derivative switches from positive to negative. Here is a graphical representation of the function. It has 4 features that are noteworthy. First, it has a left endpoint at x equals negative square root of 18. It has a right endpoint at x equals positive square root of 18. In the graph, it's evident that the left endpoint is a relative maximum and the right endpoint is a relative minimum. We will look at what the theory has to say about these endpoints in a few seconds. Our relative minimum at -3 is actually a global minimum, and our relative maximum at x equals +3 turns out to be a global max. Here is that reclassification. At -3, we have a global min, and at +3, we have a global max. Here is the first derivative test for local extrema for endpoints. If we have a left endpoint and its derivative is negative, that endpoint is a local or relative max. If we have a left endpoint and the derivative is positive, then that endpoint is a local minimum. For the right endpoint, these are opposite. If the derivative is negative, it is classified as a local minimum, whereas a positive derivative classifies the right endpoint as a local maximum. Going back to our example with the 2 endpoints, the left endpoint at negative square root of 18 is classified as a maximum since the derivative is less than 0, is negative. The right endpoint, occurring at the square root of 18, is classified as a minimum since the derivative is also negative at that point. Last example for today is a piecewise defined function. The first piece of the function is 3 minus x squared whenever x is less than 0. The second piece of the function is x squared plus 1 whenever x is greater than or equal to 0. To help us out, I provided a graphical representation. Note that the function has a discontinuity at 0, a jump discontinuity. So the first 3 pieces where we take the derivative and set it equal to 0 do not apply in this case because the function is not continuous at 0. We can, however, take the derivative and study the endpoints. To take the derivative of the function, you just take the derivative of each piece. The derivative of 3 minus x squared is negative 2x. The derivative of x squared plus 1 is positive 2x. Note that the intervals do not change. For the top piece, it's still x is less than 0. For the bottom piece, it remains x is greater than or equal to 0. There are two intervals of note. X is less than 0 and x is greater than 0. Now these are the intervals of note because these represent the endpoints. Again, I have three columns, one with f, one with the derivative, and our conclusion. To figure out the sign of the derivative, plug in points for the given intervals. For the first interval, x is less than 0, I try -1. To figure out the value of the derivative, I use the top piece of the derivative and plug in -1. -2 times -1 is +2. That means the derivative is positive on the interval x is less than 0. For the interval x is greater than 0, I pick a test point of 1 and evaluate it at the bottom piece of the derivative, 2x. So 2 times 1 is 2. That means the derivative is also positive there. The conclusions that can be drawn. X is less than 0 is a right endpoint. Since it's a right endpoint and the derivative is positive, we classify that endpoint as a relative max. X is greater than 0 represents a left endpoint. The derivative is positive for this interval, and because it's positive, we classify the endpoint as a relative minimum. To summarize the first derivative test for a local extrema, you want to compute the critical points of a function. To do this, you take the derivative and figure out for which values of x the derivative is 0 or undefined. Then determine what the derivative is doing in intervals around these critical points. Use a table to keep you organized. Finally, draw appropriate conclusions by using the table and a sketch of the function.